welcome to this talk. As I said, my name is Michael. I work on Go Protobuf. In terms of what awaits you, I'm going to start with a brief 5-minute refresher on what Protobuf is, because I don't expect that everyone in the audience has used it. So I want to just give you like a little bit of anchoring, so as to not lose you when I talk about what we have recently newly released, which is the Opaque API. And then the Opaque API, you could have also read about it in the Go blog, which hopefully you're subscribed to. But one thing you couldn't read in the Go blog about is how we then actually migrated millions of lines of code to use the Opaque API. So hopefully at least that bit will be new to everybody. All right, so let's start with the refresher. If you open up protobuf.dev, the official website, or Wikipedia, you might find a definition that goes as follows. Protobuf is Google's language-neutral data interchange format. And every word in here is pulling some weight, but let's just focus on language-neutral. So that means that across different programming languages, you can use Protobuf to interchange data. The word format hints at that Protobuf has its own wire format. And interchange, lastly, hints towards the intended use case. So Protobuf does not aim to be like a super optimized column storage for your database. No, the idea is that you interchange data. So it's at the output and at the input of your systems, not as part of your computation. So then let's look at a typical use case. So we would define the data that we want to encode and decode in a .proto file. So this is like a schema definition file. And if you've actually used Protobuf before, you might already be surprised by the first line, because typically you would expect something like syntax equals proto2 or syntax equals proto3, and now it says addition equals 2023. The answer is that there used to be a version 2 and there used to be a version 3. We're not going to release version 4 or version 5. We're just going to release yearly additions from now on going forward. And the big thing about the additions is that everything that an addition can change is codified in features, and we can automatically migrate from, let's say, edition 2023 to edition 2024 without changing behavior by just hard-coding the options that you need into your proto file. So this is a very nice, smooth migration path over time. For now, let's just remember that edition 2023 is the new way to start a proto file. Then we have a package log, which is for namespacing if you have many different messages. But in our case, we'll just have one simple message that we define as message log entry. You can see it has 3 fields. So it has a backend server, which handled the request. We have a request size and an IP address. And you can see that all of these fields are actually typed. So the request size can never exceed an unsigned integer of 32 bits. Whereas the backend server can be an arbitrary string, right? It really depends on how you want to model your types. So the workflow of using Protobuf is as follows. So you create the .proto file. This is what we've just seen on the slide. Then you feed this .proto file to the proto-C, the Protobuf compiler, which will generate code based on the file. You then take that code and you compile it into your project. And then, once you have that in your project, you can use the proto libraries to then serialize and deserialize data. How would it look like in your Go program? Let's take a pretty simple example here. This could be a hypothetical logs analysis pipeline. So it would have essentially a big for loop. I have elided the rest of the boilerplate here. But in the for loop, we would read a record from network or from disk. And then we declare a variable of type logpb.log entry. That's like the log message that we just declared in the .proto file, and proto-C has actually generated that code for us. Afterwards, we call into proto.unmarshal. That's the method that we use to decode a message from wire format. We handle the error, of course. And then the only thing that this particular program does is it aggregates by IP address. So it's just a very simple aggregation. And at the very end, after the loop has completed, we would maybe store an aggregated statistics report. All right, so now that you roughly know how to use Protobuf, you might be thinking, why would I not just use JSON, right? And the answer is multifaceted. And as a little historical tidbit, both JSON and Protobuf were actually created in the same year, in the year 2000. And back then, people wouldn't ask, why not just use JSON? They would ask, why not just use XML, right? And so you can see some of the feature set of Protobuf is sort of very lightweight XML, for example, like the schema validation that is built into Protobuf. So if you're looking to build like backwards and forwards compatible services, maybe that's the appealing part for you. Another difference that I personally like is that Protobuf has much cleaner type semantics. So for example, if you encode an int64 on one computer in one programming language, you can be very sure that what comes out in a different programming language on a different computer is also an int64. And if you've ever read the JSON spec, you will see that numbers are just arbitrary precision floats, so who knows what's going to happen in different implementations. I mean, in practice, it's probably fine, but it just does not fill me with confidence that like basic elementary integer types are weird. Anyway, the main reason why people in practice choose Protobuf nowadays, I think, is because it just encodes and decodes much more efficiently. So this means that it's faster in serializing and deserializing, and it also produces smaller output. It produces binary output, which can be an advantage because it's more efficient, and a disadvantage because it's less inspectable. So JSON is very nicely human readable. It's just strings. So if you're like writing a toy hobby project, you would probably be better off just using JSON because it's so easy to just debug it, right? But if you build like a, I don't know, multi-million-dollar computation thing, you don't want to waste your precious dollars on JSON formatting, right? You would want to have an efficient solution. Anyway, so we can debate this in more detail later, but for now, let's just say we have valid use cases to use Protobuf. Let's focus on what we have recently released. So back in December 2024, I hope some of you have seen this, we released the Opaque API. And let's quickly anchor ourselves in where we are. So this is the workflow that I just showed you, right? And in terms of what changes, the .proto files are still exactly the same, right? The only change that they might have is that they opt in to now use the Opaque API. This will change in the next edition, by the way. Then you won't even need the opt-in. Then we have the code generation step. This is what changes. So the Opaque API is a new version of the generated code. The rest doesn't change. You still compile this code into your project. You still use the same proto.unmarshal that we've just seen on the slide. Nothing like that changes. It's only the generated code that changes. Now, why does it change? Let's have a look. This is an example of the old OpenStruct API. So this is from before we did our release. And what you can see here is that the message that we declared on the earlier slide results in this Go type. So we have a package, log pb. This has been generated by ProtoC. We have the log entry struct, and it has the 3 fields that we've declared. We have the backend server, request size, and IP address. And for each of these fields, there is a corresponding getter method. And the getter is both nil safe, like you can call it on a log entry that is nil, and it will not crash. And it also returns the correct default. So if the backend server field is not set in your message, but you've declared a default value, then you'll get it from the getter. Whereas if you directly access the field, you wouldn't get the default value. Anyway, so let's briefly zoom into the concept of field presence, because we'll need this to understand what we're changing about the generated code. So field presence means whether a message field is set or not set. And Go Protobuf decided to model field presence by using pointers. So that's why all of the fields that we had in the previous slide in that struct were all pointer types, pointer to a string, pointer to a uint32, and so on. So what does that mean in practice? In practice, it means if you wanted to set the backend server field to the string zurich01.prod, the way to do it is you would directly access entry.backendserver, and you would need to give it a pointer to that string. And an easy way to do it is to call the helper functions that we have in the proto package, where proto.string, the only thing it does is it allocates a variable and then it gives you the address to it, right? So in this case, you would set the field, and then it contains zurich01.prod. If you wanted to set the same field to an empty string, you would need to do the same thing, still call proto.string, but with an empty string. So it's a non-nil pointer, but an empty string. And if you wanted to clear the field, you would need to set the pointer to nil, right? OK. Now that we know this, this might actually surprise you. Like, you might have used Protobuf and never seen any pointers. And then you might go, what are you talking about? Let's do a brief history lesson. So Proto 2 used explicit presence. This is the thing I've just been talking about with pointers, right? Then Proto 3 came along, and Proto 3 introduced a concept called implicit presence, where we would no longer need to use pointers, so that part is nice. But how do we then know that the fields are set? And the answer that Proto 3 offered was that a field is considered set if the value is different from the 0 value of that field, right? So because unset fields are not even encoded on the wire, this means if you have a message that just contains a Boolean, the 0 value for a Boolean is false. So if you just have false, it will be like an empty message on the wire, right? And like people didn't really like it. So people wanted to distinguish between true, false, and unset, and not introduce a tri-state enum for every bool where they also wanted presence semantics. So later on, Proto 3 added explicit presence after all, and it did so by using the optional keyword, which previously just was forbidden in Proto 3, and now it's used for explicit presence. Anyway, Edition 2023 has seen the light and reverted course back to explicit presence by default, and I expect that it will remain explicit presence from here on out. Okay, so now that we have that out of the way, if you ask me to characterize what the Opaque API actually introduced, this is the way I would phrase it. I would say the Opaque API uncouples the generated code API from the in-memory representation. What do I mean by this? So previously, you could just directly access the backend server struct field, right? So the in-memory representation was exactly also the public API. You could directly reach into that same memory storage. In the Opaque API, this is no longer permitted. So now, instead of the backend server field being at your disposal, you can see that the field actually has an xxx underscore hidden underscore in front of it, just to be very clear that you should not be accessing this field, even if you tried. And these fields are no longer exported, right? So unless you resort to unsafe tricks, you can't even get at them. In addition to the getter method, which we had before, we now have additional methods that allow you to do the things that previously were sort of modeled via pointers. So now we also have a has backend server and a set backend server and a clear backend server, right? But now it's up to us to sort of define the implementation of those APIs. So why did we introduce the Opaque API? Well, I just talked about pointers, and the big downside of pointers is that they add a 64-bit word for each field, right? So that's a huge overhead. If you only have one bit of information, like is a field set or not set, now you need to use 64 bits to encode that. It's obviously not efficient. So the Opaque API instead uses bit fields for presence, with the little caveat that it only does it right now for elementary fields, because the optimization is currently less profitable for other types. But notably, that might change in the future, because now we have uncoupled the in-memory representation from the API, so now we're free to do further optimizations. And it's not just that pointers use more storage space, also the fact that in order to obtain that storage space, we need to do allocations means that that's quite a slowdown. Many of you will have done a little bit of Go performance optimization, and one of the idioms is that if you can reduce the allocations, you will massively improve performance regardless of whatever else you do, right? So in this case, I've put here on the slide a couple of bench stat results from representative use cases from Google Production and Google Search, a couple different ones, and you can see that the allocs per op, in one of the cases, they're actually identical. Like this is one of these use cases where most of the messages just don't have that many elementary fields, right? Like they're mostly nested or mostly strings or something like that. So you don't see much of a change. But in the use cases where you do see the change is actually quite dramatic. Like we're doing half the amount of allocations as we did before. So that's quite a drastic speed up. All right, as I mentioned, now that all field access has to go through accessors, this actually opens the door to another optimization that we could implement, which is lazy decoding. With lazy decoding, the idea is that we can safely delay the decoding work until the field is actually accessed. However, the message still needs to be verified at unmarshaled time, because if you paid attention, you will have seen that all of the accessor methods do not return an error, and you don't want to handle an error in every accessor. So you still want the unmarshal function to tell you if the message is not correctly formed. So we still need to verify it, but we don't need to fully decode the message. So that's faster. But it's very use case specific. So for an application where you read a protobuf and then you use the entire protobuf, obviously you will not gain anything from lazy decoding. But if you have an application, let's say maybe a logs analysis pipeline like the one that we've showed previously on the slide, these analysis pipelines might look at one part of the message and then immediately discard the entire message or a large subset of the message tree. And in those cases, which they just happen over time, right? Because I told you that Protobuf is about data interchange, so by definition, it means multiple teams working on systems together. So, maybe you will have a message definition which is just so convenient to extend, and then over time, more and more is in there. And eventually, you'll have systems that don't need all of that data, right? And lazy decoding helps in those use cases. Also, the new API prevents various safety mistakes, like accidental sharing through the pointers or incorrect pointer comparison, and also accidental use of Go reflection on protobufs. In the interest of time, I'm not going to go into all of them here, and you can read up on them on your own time on the Go blog in the Protobuf Opaque blog post. One more thing I wanted to mention on the motivation part here is that more optimizations will be possible in the future. In particular, one very interesting thing we're looking at is to use profiles so that we can choose the best representation, not globally, but for your specific program. Like previously, if we wanted to optimize Protobuf for one use case, let's say in search, and then another use case in ads had very different performance characteristics, we would have to sort of balance the trade-off between the two. And if we can use profiles, then we can use the additional information we have about your use case to make better decisions at compile time. So that's a very interesting avenue for further optimizations, and that's now unlocked thanks to the Opaque API. Anyway, as I said, you can read up on that on your own time. Let's talk a little bit about the stuff that you cannot read up on, which is how did we migrate our well over 100 million lines of Go code to this new API. So just for context, at Google, you will probably not find like a non-trivial program that doesn't use Go Protobuf, like maybe only like little parts of the build system that generate stuff from one format into the other. But any non-trivial program will use Protobuf, right? So when I say we had to migrate all users of Protobuf, that essentially means we had to migrate all Go code at Google, right? So quite the undertaking. If you don't really know what the migration entails, you can read up on this on protobuf.dev in the migration guide. I'll very briefly mention that there is a tool which does most of the work for you, or at least that's the idea, and if it doesn't work, please file a bug. The tool is called Open to Opaque. The name comes from OpenStruct API, that's the old one, to Opaque API, that's the new one. And it has a couple of subcommands, the most important one being the rewrite subcommand, which you feed one or more Go packages, and then it will load them and update the code. As part of talking about code rewriting tools, I wanted to mention what I call the complexity ladder of changing Go code. Quick show of hands, who here has written a program that modifies other Go code? Okay, that's about 5 people, nice. So one thing that is really nice about Go is that because almost everybody uses Go FMT, the code is formatted the same way. So that means that even with like the entries on the very left of the complexity ladder, you can get surprisingly far. Like you've all used search and replace in your editor, so that would be like just strict textual patterns. The next step up on the complexity ladder is using regular expressions, and this really is where we can be very thankful for GoFMT, because if you've written regular expressions to match C code, you will know that there's so much variation that is very, very hard. But you actually have a fighting chance in Go with regular expressions. Once you exceed the complexity level of regular expressions, you would typically reach for the AST, the abstract syntax tree. And this is a common data structure that all of the compilers for all of the programming languages use. So they read a source code file, and then they build an abstract syntax tree, which is essentially like the machine representation of the source code. Now, if you read a source code file, that file can be entirely independent of your Go project. It could be just a standalone file. It might not even compile. You could still build the AST for it. If you go one step further, though, if you go to the typed AST, now you no longer need just a single Go file, you need the entire package. So you need all of the Go files that declare one package, and then you can build the AST of all of them, and then run the type checker. And that gives you more information, because previously in the AST, when you encountered an identifier, you couldn't necessarily say, oh, it's of this type or of that type, right? You could have heuristics, but with the type-checked AST, you know for sure. So that allows you to build more precise tooling. And then lastly, this step is rarely taken. Like if you go further than a type-checked AST, you typically go towards whole prog analysis, meaning you have the whole program available, meaning all of the packages at once, which also means that your analysis or rewrite program has to scale to the largest programs that you have, which can be a challenge. All right, so open to opaque, our code rewriting tool, it uses largely the Go standard library, and it operates at the level of a type-checked AST. In order to do our transformation, what we use is the go/parser package from the standard library to read in the code and build the AST. Then we use the go types package to do the type checking. We use the go AST package to make the changes that we want to make. And then we use one package that isn't in the standard library, which is Dave's DST package, which stands for Decorated Syntax Tree. And the only difference here is that whereas the Go AST package has rudimentary handling for comments, there are quite a number of cases where your comments might get lost. That's obviously not acceptable for rewriting code at scale, so we need to use the DST package, which keeps track of all of the comments in all of the positions. Now, the Go team is aware of this limitation, of course, and hopefully in a future version, the standard library's Go/AST package will also be able to fully deal with all of the comments. But for now, this is part of the toolkit. When you write a powerful Go rewriter, you most likely need to reach for the DST package. And then lastly, we use the Go format package to turn the AST or DST back into Go source code. Now, this is sort of the AST level thing, and in order to obtain a typed AST, what we do is we use another package from the X repositories, which is called go/packages, and this is very handy because it is a tool to load entire Go packages. Now, in the open source ecosystem, this will use the Go tool that you all use to like install, test, build, and so on. But in corporate environments, it actually has integration points to integrate with other build systems like Blaze that we use at Google. So by using the Go packages package, we can write code that works internally for our developers, but also externally for open source users like yourself. All right. With regards to complexity, I explained the complexity ladder, but I want to point out that Open2Opaque is a particularly complex rewriting tool. I would even go as far as saying it's the most complicated rewriting tool I've ever worked with. It is a multi-pass rewriting tool. So what does that mean? If you have source code like the one at the top of the slide here, where you assign entry.backendServer into a temporary variable f, and then you check if f is not equals nil, and if so, you modify the contents of that field. Then the Open2Opaque tool will have multiple passes that are involved in ultimately generating the correct code. The first pass is the has pass, which recognizes the pattern of checking that a pointer is not nil and replaces it with entry.hasBackendServer. So far, so good. But now this pass, instead of re-implementing all of the logic of the other passes as well, just figured, OK, it's easier if I just turn the f into entry.backendServer, at which point in the next iteration, the set pass will actually pick that up and rewrite it into the proper setter call. So the tool kind of converges, and that is definitely more complicated than any other rewriter I've ever seen. All right, so now we have a tool. What do we do? Do we just tell all of the other developer teams at Google to migrate their code and then wait for them to be done? I mean, no, obviously not, right? Instead, we have what's called the churn mandate. This is a policy whereby within engineering, 80% of the migration work needs to be covered by the team that introduces the migration. Whereas 20% of the work can be pushed onto others, like that cost can be externalized because it doesn't always make sense for like a central database infrastructure team to do these very complicated end product migrations. But on the other hand, it also doesn't make sense for every product team to become an expert on the database to do a simple migration. So the insight here is that the team that designed the migration is also in the best position to actually do the migration, or at least shepherd the migration. And that's why they have to bear the bulk of the cost. I think that's a very sensible approach. So this is the policy side of things, and then there's also the process side of things, whereby we also have a team called the Large Scale Changes team, the LSC team, and that team helps with expertise, with process reviews, like maybe you should be using a different rewriter that you've never heard about, but it covers your use case and more. And most importantly, they have a special power called global approvers. So you might have heard that at Google, all of the code is in a mono repo, meaning we don't have like many thousands of Git repositories, we just have like a giant repository. However, it's not that anybody working on that repository can change everything. No, there is a layer of ownership. So some parts of the code base will be owned by, let's say, the production team or the ads team or the search team. But with the global approval power, you can approve any change, even if you're not a regular owner of that, right? And the LSC team consists of like senior engineers who have experience with large-scale changes and can very efficiently review like large batches of changes and then point out like unsafe patterns and stuff like that. So this is the route that we went. But there's like a couple of steps missing here, right? So I only told you that we have a tool, but how do we scale this up? Well, we combined the Open2Opaque tool with MapReduce and turned it into a nightly pipeline. So we just run this every night on all of our code. And luckily, because it's a type-checked AST that we need, we don't need to actually build all of the code, but there's like a different static analysis team that already does that. Like every night they take all of the code and just build it all. And we can just take that build result and then type check from that. So it's a lot less computationally efficient for us, and it is a huge advantage to have this sort of nightly analysis, because now we can actually query dependencies and produce helpful reports. A common question by product teams might be, well, we actually want to adopt the Opaque API, but there's like a lot of code in my dependencies that might need migration first because they share protobufs or something like that. Which other files do I need to migrate first, or for which files do I need to wait, right? And also, we can aggregate these numbers and have like a nice dashboard for the current status of the migration, which is very nice for motivation, both internally within our team of engineers and also like for managing upwards for like leadership to tell them, look, this is how it's going, right? All right, so the next step then is we not just want to analyze all of the code and produce reports. I mean, that's nice, but we actually want to change all of that code. So in order to rewrite the code, we once again updated that pipeline and made it also produce diffs. And then we feed these diffs to yet another internal tool. So you can see we have quite a lot of tooling here in this space, which you can kind of think about like if you've used GitHub, you will have maybe seen these Dependabot pull requests where they have an automated tool that like updates your dependencies to the latest version if there's security issues. And we have kind of a similar tool where you just feed it all of the diffs that you want to see done, and then it will take care of doing all of the pull requests. Like in our lingo, it's obviously not pull requests because it's not Git, but it's the same thing, right? So it will send out all of the reviews. In our case, it will send out the reviews to the global approvers, and then they just get like hundreds of these reviews every day. They have like batch review tools. They go through these very efficiently, and then that's how you can sort of change a large code base with like hundreds of changes every day until you're mostly done. All right, so let me briefly summarize. And then if you have any other further questions, we don't have time for Q&A as part of the presentations, but afterwards, feel free to just ask me. I'm happy to talk about this stuff some more. But let's quickly go through the wins. So we have saved hundreds of thousands of CPU cores through the efficiency improvements at Google alone. And other companies we know have sizable Protobuf deployments as well. So if you look at others like Uber, Twitch, Cloudflare, etc., we hope that they can also adopt the Opaque API and save some more CPUs worldwide that way. We have also landed over 100,000 commits with Go code changes for this effort, which I believe was the largest code rewrite we've done at Google, at least for the Go code, aside from entirely mechanical stuff like Go thumping the entire code base whenever Go thump changes a little bit. That's obviously a lot less complicated, right? Because you're not potentially changing semantics, whereas here the code changes are a lot more involved. And then we have over 98% of Google's production workloads on the Opaque API already, just in case you were wondering, like, is it ready for usage? And also this tells you that all of the further optimization on Protobuf will be gated on the Opaque API, because that's what we use, so that's what we optimize, right? So lastly, I can just say we hope you'll migrate to the Opaque API too. If you have any questions or you would like further information, you can go to protobuf.dev for the official website, or as always, the Go blog, which again, I hope you're all subscribed to. So with that, thank you very much.